Poincare recurrence, this notion of, or this question of whether or not the universe is in a box has recurred many times throughout our conversation. And a few minutes ago, you mentioned inflation and problems with inflation. And this makes up a substantial, maybe a chapter or two of the Janus point. But for those who aren't familiar with the notion of inflation, what is it? What important empirical phenomena does it explain? And what are its lingering problems that you were alluding to that leave an opening for an alternative proposal?
The problem of inflation, I guess the history of it comes in around the late 1960s. This is after the microwave background. So cosmology was completely transformed by the discovery of the microwave background in, when was it, 1964, 65, that there is this radiation at about 2.7 degrees centigrade, very absolute Kelvin, 2.73 Kelvin. Very, very low temperature. But there's thermal radiation all around us. And it had been predicted, and it was found by accident. And that completely transformed cosmology. And the picture that then developed, the simplest model of cosmology, predicted that the universe would be completely uniform, that it would be born completely uniform. There would be no structure in it at all. And without structure, you could not have the formation of galaxies and things like this. So there were two very important papers in one in 1968 by an Englishman called Harrison, who had moved to the United States. And it was followed by, 2 years later, by the Russian Zeldovich, with saying, there's a problem. We don't know where the structure would come from, but to create galaxies, the structure would need to have a particular form. Well, it's called a scale invariant potential. So the question was, where could that come from? Where could that structure come from if it wasn't really there in the start? So that's the birth of the problem. And what then happened was Alan Guth, in his doctoral thesis in I guess, was it from about 1975 or something, he was working on things in particle theory where there was a theory that magnetic monopoles should exist. These were very sort of exotic things. And the theory that existed at the time suggested they should be all over the place, but there was no trace of them to be found anywhere in any experiments. Nobody found anything. And Guth realized that there was a special type of force which could make the universe expand incredibly fast. And so he thought, this could explain why we can't see any magnetic monopoles, because their density has been greatly reduced. And then there was another problem which Bob Dicke, he was the person who had predicted that the microwave background would be discovered and was about to build a machine to detect it when it was found just up the road, about 30 miles away from him at wherever it was. Dicke was in Princeton. I can't remember where the discovery was made of the microwave background, but Dicke had pointed out what's called the horizon problem. So the microwave background had an incredibly, it still does, has a very uniform temperature wherever you look in the universe. It's thermal equilibrium to a very high degree. But the then existing theory of the expansion of the universe showed that if you went back, the universe would never have had any opportunity to equilibrate, to get into thermal equilibrium. So this is called the horizon problem, and it is still sort of there. I mean, somehow or other, a theory's got to explain why the microwave background has the same temperature in every direction. Just the mere fact that the temperature was the same, twice the moon's diameter or something like that was a major problem. So Guth then thought, well, maybe the universe did have a chance to get equilibrated right at the start, and then was also producing these magnetic monopoles and this ability to expand the whole universe very fast. And then that would solve two problems at once, kill two birds with one stone. So he then, I think it was 1980, he published a paper where he coined the expression inflation. And then in 1982, there was a very famous workshop in Cambridge in England, which a lot of really significant people, including Stephen Hawking and others, were present, and Guth presented his ideas. And then they realized that in a very rapidly expanding universe, if the right conditions were, you still had to have the right conditions at the start, you could get these Harrison-Zeldovich fluctuations to be created as quantum fluctuations. There's quite a lot of technical stuff going into all of that, but the very rapid expansion was an important thing, and then it had to start. And in fact, Paul Davies, who's a very solid scientist, and his student Bunch had established that there could be they'd found that in de Sitter space, one of the solutions of Einstein's theory, you could have a vacuum, which is now called the Bunch-Davies vacuum. And then it was found in 1982 that this very rapid expansion would transform the Bunch-Davies vacuum into Harrison-Zeldovich fluctuation. That's the broad picture. So this was seen as a huge success, and there was huge excitement because it seemed to suggest that quantum theory would explain the huge macroscopic structure of the universe, why the stars and particularly why the galaxies are there. So this was hugely exciting. However, it did require sort of fine-tuning. The conditions at the start had to be right, and so they introduced something called an inflaton, which had to have rather special properties. And I remember going to lectures in Oxford in about 1992, so about 30 years ago, where the speakers had made it very clear, look, inflation is an unsatisfactory theory because we don't have a first principles theory of what is at the start, what is the inflaton, and how does the expansion all get started. What happens, he said, is quite clear. We make observations now, and from the observations now we say what must have created them. But that's just putting the answer in, getting the theory out of the answer, not having a theory and then getting this was so different from Einstein's theory, who in 1915, he'd predicted that the light deflection of stars light from the stars passing the sun would be exactly twice what Newtonian theory predicted. And that's what Eddington confirmed in 1919 and made Einstein a world celebrity overnight. There's nothing like that in inflation at the moment. And I think although I don't engage in intense discussions about this, but sort of just following the things, I think an increasing number of people are getting worried about inflation and saying it's a bit tricky. And then there's a significant problem how it all gets started, because although the great thing is that it's changed. The story has changed a bit. Now you have to have a part of the universe, a certain amount of the universe, which is initially uniform for it to get going, and one doesn't know how it starts. So I don't want to be taken for a world expert on this, because I'm not. I just listen to what people say and pick up things and read the odd article. But I don't think I think it's a common it's a common view among quite a lot of people that inflation is getting a bit problematic now. So that's it. But what I'm saying in the genus point is that if the Newtonian theory is any guide, at least in these Big Bang Newtonian solutions, which, by the way, the theory was incredibly beautifully developed in a paper published in 1918. That's 11 years before Hubble published his result on the expanding universe. The whole theory of the Newtonian Big Bang was developed in most marvelous mathematical detail in 1918 by a French mathematician called Jean Chazet. And that suggests that the Newtonian Big Bang starts very uniform and then gets structured. You don't have to put in uniformity, and you don't have to put in inflation. You don't have to put in anything. You just take those Newtonian solutions and do it. Now, when I talk about this, no experts are taking me particularly seriously. Some of them do they are interested. But the acid test is to get the fine details right. You have to get what. So Harrison and Zeldovich said that you have to have a diagram, a spectrum which rises linearly with a slope exactly 1. But then it was suggested that the slope might be slightly less than 1. Instead of being 1, it might be 0.95, 0.96. Well, this, in fact, is exactly what is observed. The slope is slightly less than 1. So that would be the absolute acid test. But now, if that came out of this Newtonian theory, which it might just do, I think it's not impossible that calculations on a supercomputer, and I am talking to two people who might be able to do these calculations, it might be possible to show that if you had a Newtonian universe with trillions of particles, that very precise structure with a slope just slightly less than 1 is sitting there. If that would come out, that would be impressive. But this is in the future. It would be nice if it comes. But certainly the Newtonian theory suggests it might be possible.
There's a terminological distinction that I think you're making, but that I'm not familiar with. So obviously when something inflates, it expands. But expansion, as I understand it, and as observed by Hubble, I think is very well confirmed. So just what is the distinction between expansion, which is confirmed and accepted, and inflation, which is being questioned?
Well, first of all, I think both Hubble, the normal way people think about Hubble's discovery, and inflation, I think there's still definitely an instinctive feeling that there is a ruler outside the universe. I think there's a lot. I think this is. I was on a radio program in Britain called In Our Time with Martin Rees, who at that stage was the president of the Royal Society. He's a very distinguished astrophysicist and a great scientist. And we were talking about the expanding universe. And I stuck my neck out and I said, for me, the expanding universe stinks. It's not expanding, it's changing its shape. And Martin was really quite taken aback. He said, Julian, well, your philosophy might be quite interesting, but I think you're forgetting 95% of the physics. I'm actually getting much more confident now that I was right. It just was that I needed to, I can flush things out better now. So what the situation now is, and about this I am confident, is from the known history of the universe, more or less the first structures that actually formed were nucleons. This is very early on. So nucleons formed, then atoms formed, and then molecules formed, and then stars formed, and then galaxies formed. Now, all of these things, once they'd formed, the sizes that they had, the ratios of their sizes stayed more or less constant. So these are all, so to speak, mutually consistent rulers. And the one thing which changes is the separations between the galaxies. So you can use all of these things, starting with nucleons, atoms, you and me, the Earth. There's a whole lot of things whose sizes have not changed significantly for billions of years. But the one thing that has changed radically is the separation between the galaxies. And that is actually, it's just really, strictly speaking, it's a change of shape. It's become the shape is defined by ratios. It's the ratio of all those rulers to the separation between the galaxies. So I'm pretty confident I was right to tell Martin that the universe is not expanding, it's changing its shape. And this is the only thing in physics that has meaning is a ratio, and people just forget this. Now, I have a collaborator who's a cosmologist. I won't mention him because he may not want me to do it, but he says that when cosmologists give lectures to students, they start off by saying, well, we can't really talk about the size of the universe, so we say that the size of the universe now is 1. That's a nominal definition. And then its size in the future is some ratio of that, or its size in the past is some ratio of that. And then he says they forget all about that statement. Just instinctively think that there is, that the universe is, that you can speak about size of the universe, whereas really it is always ratios. It is always ratios, and people just forget this. I mean, as I look at you, if I just look at you now, your head is and the cat is a fraction of the picture behind you on the wall. These are objective facts, and you can never. Scientists never get away from that, and it's just staggering to me that a large number of cosmologists and physicists and so forth just forget that fact.
So, to help me better understand then what you mean, for what would it take for you to say that the universe is expanding? I know that the first law of thermodynamics is that energy is not created or destroyed, but would you say the universe is expanding then if more mass were added to the universe? Is that the sort of thing that would make you say that the universe is expanding? Or is the universe just the sort of thing that can't expand based on your terminology?
I think it's just meaningless to say that. I think the universe is changing its shape. It's just getting more structured. Yeah, that period, that's it.